Hello students, today we will discuss about group 18 elements. Okay, group 18 elements, or these elements are also known as noble gases. Okay, you know there are 6 elements present in group 18 of long-term periodic table. Okay, these elements, such noble elements, are present in group number 18 of your P block. Okay, what are these elements? Let us write down these elements. First one, that is helium, next one neon, next one argon, next one krypton, and next one xenon, and the last one, that is in the list, that is radon. Okay, so these are known as your group 18 elements. Okay, so let us mention their atomic number. So helium, you know, 2, then you just add 8, that will be 10, then you just add again 8, that will be 18, 2, 8, 8, next magic number, that is 18, you will get 36 over here. Next you just add 18, that will be equal to 54 over here. Okay, next 32, that is incomplete, just add it, that will be equal to 86. Okay, now such elements correspond to the general electronic configuration, that is these elements corresponds to the general electronic configuration, that is NH2NP6 full field configuration. Okay, since you know all these elements are present at the end of each period in the long term periodic table, so their general electronic configuration, that is NH2NP6, except helium, you can mention over here, that is 1s2. Next near, after helium you are getting 2s2, 2p6, and in case of argon, again after the electronic configuration of neon, you are getting over here 3s2, 3p6. Okay, and next, that is krypton, you can mention over here argon, and next is 3d10, 4a2, 4p6. Okay, next, that is xenon. After krypton you are getting over here 4d10, 5s2, 5p6, and the final one, that is radon, you are getting over here after xenon. Okay, so the configuration will be 4f14, 5d10, 6s2, 6p6. Okay, so now we just focus their valence shell configuration, which is in the form of NH2NP6, 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 NH2NP6. Okay, so all the valence shell orbitals are fulfilled by electrons. That means these elements have completely octet. That's why their valency is taken as 0, and most commonly such elements are known as zero valent elements. These elements are known as zero valent elements. elements because their valency having 0. Okay. Again, due to zero valency nature, neither they combine with themselves or with any other elements to form molecules or compounds. Okay, that's why these are chemically inactive in nature. Okay, due to zero valency, such elements are chemically inactive in nature. Okay, that's why these are regarded as inert gases. That's why these are known as inert gases. And you know the special characteristics of group 18 is all the elements are gases. Okay, in group 18 all the elements starting from helium to radon all are gases. All elements exist as gases. All elements exist as gases. So these are called inert gases. These are also called zero valent element. Okay. These are also called as rarer gases. Rare gases, why? Because such noble gases are present in very minute amount in the atmosphere. Okay. Next, we will go through their occurrence. Occurrence. First one, air. In air, except radon, all other elements are present 1% by volume in the atmosphere. Okay, and we remember that argon is the most abundant noble gas found in atmosphere. Okay, and second occurrence if you consider, that is from spring water. Okay, some spring water also contain very small amount, also contain in minute amounts of helium, neon, argon. Okay, and third source, that is natural gas. Okay, certain natural gases found in certain region of America and Canada contains 2 to 7% of helium. Okay, and the last source, that is your from radioactive minerals. For example, if we consider the decay of radon, array 88 having mass number 26, on decay it emits an alpha and helium particle. Okay, so that is equal to plus He24, and it will give you radon, that will be 222, and here that is 96. Okay, so these are few occurrence of such noble gases. Okay, so right now we will go through. It's very important that they are general trending properties, general trending physical properties, you can say. It's very important, that is general trending physical properties, general trending physical properties. Okay, so very simple. The first one, that is atomic rating. Atomic rating. You guys tell me, along a period, you know, the last element is nothing but your noble gases. In each respective period, whenever you move from left to right, then the last element of each period is nothing but your inert gases or zero group elements. Okay, so you know, whenever you are moving from left to right in a period, then atomic rating, okay, what happens? Atomic rating decreases. Okay, so from this it is clear that each noble gas having smallest size with its respective period. Okay, so from left to right, atomic rating decreases. Okay, and that's why the atomic radii of noble element in its particular period having smallest size. However, from top to bottom, atomic radii, what happens? Decreases. Why? Due to increase in additional cells. It's very genuine. And next, second characteristic property, that is you can consider, that is ionization energy. Tell me again, I am back to their electronic configuration. They obey very stable electronic configuration, NH2 NP6. It is very difficult to remove an electron from balancer because of this octet configuration. Okay, and you know, from left to right, the atomic size of noble element is very less. That means due to high effective nuclear charge, electrons are strongly bounded by nucleus. Okay, so in a period, the ionization enthalpy of noble gas element will be maximum because they have stable electronic configuration, and in order to remove an electron, you have to supply high amount of energy. That's why they correspond to high ionization energy. And again, this ionization energy decreases down due to increase in atomic size. That clear? Next, that is electron affinity. You see, again, same concept over here. They having configuration NH2 NP6. Again, due to its stable configuration, it is very difficult to remove any electron from these subcells for the incoming electron. So if you need to do this, then you have to supply energy over here. So electron affinity or electron gain enthalpy in case of noble gases is found to be positive, and this positive value decreases the electron gain enthalpy. The positive electron gain enthalpy value decreases down the road because of increase in atomic size. Is that clear? So next property, that is solubility. So regarding solubility, these are sparingly soluble in water. Sparingly soluble in water. However, this solubility increases down the group due to increase in atomic size. Okay. Then next important characteristic, that is liquefaction. It is very difficult to liquefy these inert gases or noble gases, because you know they are pure gases and they are characterized by very weak van der Waals force of attraction. So it is very difficult to condense the gas molecules in order to convert it into their liquid. Okay, but however, whenever you are moving from top to bottom, that is from helium to radon, top to bottom, then what happens? Atomic radii go on increasing. So due to increase in atomic radii, so van der Waals force also increases, so that the liquefaction becomes easy from top to bottom. Okay, this is regarding liquefaction. Next, that is they are melting and boiling point. You know, since all these are gases, so they have very low melting and boiling point. On moving from top to bottom, since the atomic radii increases, that's why, and van der Waals force, magnitude of van der Waals force is characterized through atomic radii of elements. So you can say the melting and boiling point also increases from top to bottom of noble elements. Okay. Next very important property, that is monoatomic gas. Monoatomic gas. Okay. So all the noble elements exist as monoatomic gases. Have you ever seen He2, Ne2, argon2? No, this form never exists, because you know they have 18 electrons due to zero valence nature. There is no combining capacity of such elements. Okay, if you remember the molecular orbital theory that you have got in first year. So in case of helium, let's say helium molecule is possible, He2. Okay, so how many number of electrons are there? You tell me. 2 plus 2, that is equal to 4 electrons. So your parents 4 electrons in different bonding and anti-bonding molecular orbitals. So its molecular orbital configuration can be written as sigma 1s, okay, less than sigma star 1s. So this much. So 4 electrons can be arranged like this: sigma 1s square, sigma star 1s square. 2 electrons here and 2 electrons in anti-bonding orbital. Okay. Now we just calculate the bond order. Bond order, that is equal to half into Nb minus Na. Number of bonding electron how much? 2. Number of anti-bonding electron how much? 2. 2 minus 2, that is equal to 0. You see, there is no bond existing in this molecule. That's why all are exist in the form of monoatomic gases. Is that clear? And from experimental data, their Cp by Cv ratio, Cp-Cv ratio also found to be 1.66, which indicates all are existing in the form of monoatomic gases. Okay. So these are some general trending properties of or physical characteristics of noble gas elements. And another thing, very important thing is there. Why such elements are known as noble gas elements? Since I have told you, due to their zero valency and inactive nature, they do not form molecules with themselves, or they can't interact, they don't participate in with other elements. Okay, so these are chemically inert, I have told you. But why such elements are called noble gas element? It has been observed in case of xenon due to its larger size and valence shell is far away from the nucleus. So what happens if it interacts with certain electronegative element like what? Oxygen, or you can say fluorine, then what happens? They have tendency to remove the electrons from the valence shell of xenon to exhibit different oxidation states. As a result, xenon has tremendous tendency to form molecules like xenon difluoride, HCF2, HCF4, xenon tetrafluoride, HCF6, xenon hexafluoride, and with oxygen, it may also form xenon trioxide, XeO2F2, okay, XeO4, XeOF4, like this oxygenated compound also form. So due to such special tendency of forming compounds with fluorine and oxygen, group 18 elements are known as noble elements, or we can say noble gases. Okay, you see, if we consider in case of xenon fluoride compounds, okay, just remember that xenon combines with fluorine under certain temperature, it will form xenon difluoride. Xenon combines with fluorine to form xenon tetrafluoride. Xenon combines with fluorine to form xenon hexafluoride. Okay, so here certain temperature conditions are there. Just remember, here the ratio is 1:2, here the ratio is 1:5, and here the ratio is 1:3. Okay, you can remember like 12, 15, 120. Okay, so formation of xenon difluoride, xenon tetrafluoride, and xenon hexafluoride. Okay, let us provide some information regarding the structure of XeF2, XeF4, and XeF6. You see, Xe54, its configuration, valence configuration, that is 5s to 5p6. So here, this is 5s, 2 electrons are there, 5p6. So this is 5p, 2, 5p6, and the vacant orbital, that is 5d. Here you can say this is ground state, xenon is in zero oxidation state. Okay, so you see fast excited state, fast excited state, what happens? This is 5s, this is 5p, 1 electron from 5p is excited into the orbital of 5d. Okay, so in second excited state, there will be 2 electrons in 5s, 1 electron, 1 electron, 5. Okay, in the third excited state, there will be 2 electrons, 3, 1, and another orbital. Okay, now if we consider the structure of 3-fluoride xenon difluoride, okay, in case of xenon difluoride, here in the first excited state, these orbitals get entangled to give sp3d. sp3d. How many hybrid orbitals we are getting over here? 3 plus 1, 4, so 5 sp3d hybrid orbitals we are getting, and 2 fluorine atoms with their half-filled orbital comes and overlap with this unpaired electron to form bond. So what will be the geometry? sp3 is a little trigonal bipyramidal, but due to presence of 3 lone pair electrons, its geometry XeF2, this one is 1 fluorine, this one is 1 fluorine, XeF2, and 3 lone pairs, 1, 2, 3, that will be given in this direction, and in this direction. So its geometry should be trigonal bipyramidal, but due to presence of three lone pair electrons, its shape is linear. Its shape is linear. Then back to second excited state. Here the type of hammer 1s 3p sp3 and that is d2 sp3 d2 into 3 plus 2 5 plus 1 6. So its hybridization should be regular octahedral, but due to presence of two lone pair electrons, its shape becomes square planar. So that will be xe 1f here, 1f here, 1f here. So this is square planar geometry, and lone pair 1 above lies one above and below the square planar plane. So its shape is square planar. Square planar. Okay, like that. Let us consider in this case, that is sp3d3 sp3d3. Okay, so here the geometry will be, or the shape will be, here the shape due to presence of this lone pair, its shape becomes distorted octahedral. Let's see, xe f f f f, and here is f, here is this f, because of lone pair electron is slightly bent in this direction f. Okay, so here the geometry you can say, the shape you can say distorted octahedral, distorted octahedral. Okay, clear. So now let us discuss few uses of noble gases. That is very important. You know, first noble gases, that is helium. SEDI was frequently using helium and oxygen mixture while they go to the depth of water. Okay, because you know helium is insoluble in blood. Okay, and you know helium also injected, that is inside balloon. Okay, and somehow it is also used in food preservation also. Okay, and in case of argon, it is used filling radio valve, and also used in rectifier. It also producing inert atmosphere during welding and for extraction of various metals. Then neon, you know, it is used to safety devices for producing electrical instruments. It is used in neon discharge lamps also, likewise. Krypton and xenon are used in filling instant metal infrared electric valves. These gases are considered superior than argon for this purpose. Okay, and radon, you know, radon is used for cancer patients. It is used to check the defects in steel castings. Photography of internal opaque materials is made with the help of radon. So these are few uses of noble gases. Okay, students. So nothing more is available in your syllabus. So you just go through that. I hope you have got it properly. Thank you. We will meet in next class. Bye bye.